Okay, these are pretty straightforward, I think. You're rolling a single die. So obviously if we drew out the set, you've got 1, 2, 3, 4, 5, 6. That's our sample space. That's everything that's possible. So there's 6 possible outcomes. The probability of rolling a 3, there's only one 3 in our sample set. So we've got a 1 in 6 chance of rolling a 3. The possibility of hitting an even number or a 5. So if we define these as sets, then we'd have a set of even numbers, 2, 4, and 6, and then a set of just 5. And they're asking us what's the probability of rolling either a 2, 4, or 6, or a 5. So in that case, there are 4 out of 6 possible ways, or 2 out of 3. Then part C says the probability of rolling a 3 or a 6. So again, if we had a set, we'd just say there's a 3 or a 6. So there are 2 possible outcomes there. So it's 2 out of 6 or 1 out of 3. And an even number that is also greater than 2. So we've got our set of even numbers. If we did our set of everything that was greater than 2, we'd have 3, 4, 5, and 6. And we're looking for the probability that you could get something that is meeting both of those criteria. We see that there are 2 options that appear in both sets. So that tells us that we've got 2 out of 6 or a 1 out of 3 chance. On to question 9. So we're dealing with a pool table and the ball's on the pool table. I've done a little bit of advanced stuff here to get it organized. So there are 7 even balls, we're told, 8 that are odd, 8 that are solid, 7 that are striped, and 1 that's white. Now we're asked, if you're choosing a ball at random, what's the probability of choosing an even numbered ball? Fairly straightforward again. There's just an even number of balls. There are 7 even numbered balls, so it's 7 out of a total sample space of 16 balls. So 7 out of 16. Solid colored ball, similarly, solid color, there are 8. So we're 8 out of 16. Now we're looking for an even numbered ball that is also solid colored. So we're told that the solid colored balls go from numbers 1 to 8. So if I use this Venn diagram over here, I could say, well, there's a solid 1, then in the overlapping area or in the intersection with even numbers, there's a 2, then there's a 3, and the overlap is a 4. Solid, there's a 5, the overlap is a 6, 7, and an 8. So I end up with a Venn diagram that shows me what's happening between even numbered and solid numbered balls. So based on that, we can see that there are 4 numbers in the overlapping area in the intersection. So for part C, our probability is 4 out of 16, or 1 out of 4. Follow a similar approach for part D, an odd numbered ball or a striped ball. So we go through and do the same thing. We start the odd numbered balls starting at number 9. So 9 is odd and striped, 10 is just striped, 11 is odd and striped, 12 is just striped, 13 is odd and striped, 14 is just striped, 15 odd and striped, and that's it for the colored balls. Okay, so we've got, again, 4 in the odd numbered ball space. So we did odd and striped, but it was actually asking the possibility of getting any odd striped ball. So for that, we would also have to include the other odd numbers, which would be 1, 3, 5, and 7. So we'd end up with 8 out of 16. So while we've got 8 odd balls, we also want to, another successful outcome is having the striped balls. So we actually have to add in the 3 striped plus all of the odd balls. Right, so the possible outcomes are 8 plus 3. Those are all of our possible successful outcomes. That's the chances of us getting an odd numbered ball or a striped ball, both of which are considered successful outcomes, and they have to be divided by the total possible, which is 16. So we end up with 11 out of 16 in total. So just to be clear, the question is asking us, what's the probability of getting an odd numbered ball or a striped ball? Part C had an implied and or an implied intersection, whereas part D is an or a union. So we needed to add all of the possible outcomes together. So question 10, we're starting off building a Venn diagram again. It tells us that we've got skiers, snowshoeing, and dog sledding. Okay, and Each student has to choose one activity. So every student is going to be in one activity. That means there's going to be nothing around the outside, right? There's going to be nobody that's outside of each of those sets. So they tell us that 10 students went skiing, 7 students went snowshoeing, and 11 students went dog sledding. Following our process for filling out Venn diagrams, we look for and statements. In this case, that's all they've given us. There are no ors in this one. This told us that 2 students choose to both ski and snowshoe. So in this case now, they don't give us an easy way of figuring out where, which side of things, which side of the lines they're going to fall on. So the intersection between skiing and snowshoeing, there are 2 people in that category. The intersection between snowshoeing and dog sledding, there are 4 people that fit that criteria. And the intersection between skiing and dog sledding, there are 3 people that are in that category. So if we look at where those fit on our Venn diagram, skiing and snowshoeing, so that's the overlap area in there. We know there are 2 people that fit in that category. What we don't know is whether they're here or here right now. So for the moment, I'm just going to put them on the line because I know they're in that area, that they have to be enclosed within snowshoeing. The next one, snowshoeing and dog sledding. So the intersection between snowshoeing and dog sledding is this area in here. Same issue. I know there are 4, but I don't know if they're here or here. So I'm just going to put them on the line for the moment. Then the intersection between skiing and dog sledding is right there. Same issue. I'm not sure which side of the line they fall on. So I'm just going to put them on the line for now. The next step, I'm going to start with one of the sets. So in this case, I'll start with snowshoeing. I know there are 7 people in that category. I know I currently have 6 people. So if I look at what's included for absolutely in that set, I know for sure in that set that there's a 2 and a 4 group of people in that set. So there are absolutely at least 6 people already accounted for in that set. So I've got 6 people already. That tells me I need to add 1 more missing. So for now, I'm just going to put that 1 out here and I'll move on to the next category. So let's look at skiing. I know I need to have 10 people. I currently have, if I look at the area, I've got 2 and 3 that are guaranteed to be in the skiing area. I've got 2 and 3 there. That means I've got 5 already. That means I need to add 5 more. So I'll put 5 more in there. Finally, dog sledding, same approach. I need to have 11 people. Right now, I've got 3 and 4 people. I have 7 people. Therefore, I need to add 4 more. Now we need to check what we've got in our diagram against the total that we need to end up with. We said that we're told that there is an omega, so our sample space is 20 students. If I add up what I've got in my diagram, 4, 4, 8, 10, 13, 14, and 5 makes 19. So I'm 1 short. So what am I going to do with that? There would be 2 possible outcomes here. Sometimes when I'm 1 short, that means I need to put somebody out here. But we've already said that the students wouldn't be on this trip if they weren't doing an activity. So they have to be doing at least 1 activity. If they were out there, it means they're not doing an activity, so they wouldn't be on this trip. So everybody has to be within one of those circles at least. Because we don't have any other information to work against this, I'm going to say they have to be in the center because that's really the only area that would make sense. However, as soon as I put a 1 there, that's going to affect these other numbers, the 2, the 4, and the 3. I've said there are 4 there already, so that 4 is the total that was going to be in here. I'm saying now that 1 has to be in the center, so that means that 4 will basically go away, and we have 3. So now I've accounted for that 4 by having a 1 in the center and a 3 in the overlapping section there. I'll do the same process here now. I've got a 2 in total that's supposed to take up this space, so that's what the total count in there is supposed to be. Since I've put a 1 in the center, that means now I end up with a 1 there, and I scratch out that 2. Finally, same thing here. We've got a 1 and a 3, so it has to be a total of 3 in this space. Since I've just put a 1 in the center, that means I have to take this down to be a 2. So now I have a total of 3 there. So let's see what happens if we do our adding up now. I've got 1, 2, 3, and 3 makes 8. So that's not right because we're supposed to end up with a total of 7. Let's take a look around here as well. Here I've got 2 and 2 is 3 and 3 is 6. and 4 is 10, but I need to end up with 11. Here I've got 5, 6, 7, and 2 makes 9. So I'm still one short. So I'm going to go ahead. And what that means then is I need to add one more here, make that 6, make that 5, and I think I did some math wrong here. 3, 4, 5, 6, and I need one more to make 7. So just to clean that up a little bit. Okay, so it's a bit of an iterative process. There wasn't any way to use algebra to solve that one. So you wanted to go through and just using the logic, write out the set notation so that you keep track of what needs to be where. Put that into your set, but don't commit to exactly where it goes. Remember, I put it on the line until I knew for sure, until I had some more information about where everything needed to be. Once I had that information, then I could commit to what the final numbers would be. And then I could go back and adjust accordingly to get the totals that I wanted. So remember, the final step is to always go back and double check to make sure that you've got the total that you need. So we've got 6, 7, 8, and 2 is 10. That's the right amount. 1, 2, 4, 3 is 7. 2, 1, 3, and 5 is 11. And now I should just add up everything in the middle. 6, 8, 9, 10, 12, 15, and 5 makes 20. And that's what we needed to end up with as our total sample space. So that gives you the complete Venn diagram. Well, remember though, so we need to end up with a total of 20, right? That's the commitment we're told. There has to be 20 students in total. However, if you added up all of these numbers, you've got 11 plus 7, you're at 18, plus 10 is 28, right? So you've got too many because some students are doing multiple events. So if students are doing multiple events, you can't put them all in because you don't know how many go in each side, right? So when I added the ski and snowshoeing, right, that's in this area, but I didn't know of that too. I didn't know at the time that they were going to be split 1 and 1, right? So that's why I parked them in the middle until I could go through the process of figuring out which side of the line they needed to be on. And I only figured that out once I realized that I only had accounted for 19 students in my diagram, right? So that told me that I was missing one somewhere, and the only place that I could add it in was right in the center. So you know what, I'll back up. You know what, why don't I just go right back? I go right back to the start. I'll just go through it more quickly this time. So at this point, all we've got are the totals for each group. As I said, that total is much bigger than what we need to have our 20 students. So we look for the intersection of skiing and snowshoeing. That's this space here, skiing and snowshoeing. We don't know which side of the line they're going to go on there, so I put the 2 there. Then the snowshoeing and dog sledding. So snowshoe and dog sledding, that's this space here. All right, snowshoeing and dog sledding. Snowshoeing and dog sledding is 4, so I have to put that on the line there. And then skiing and dog sledding. Skiing, dog sledding, the intersection is here, so I put 3 there. Once I've got that, then I think about the totals, right? So snowshoeing, there have to be 7 people. Right now, I've only accounted for 6, right? This 3 is on the line, so we don't know for sure that it's included in snowshoeing. So we're just adding up everything that we know 100% has to be in snowshoeing. And we have that information from these intersections. So I know that there are 6 that have to be in snowshoeing, but I'm definitely missing 1 because I have to end up with 7. So if I have to end up with 7, I'm going to add 1 more in. And like I said, at this point, because I know I can't have people outside of the sets, I'm not allowed to add the 1 there. So I'm going to put the 1 in the middle. Once I put the 1 in the middle, that causes the cascading effect of say, okay, if I have to have 4 in total, that means there are going to be 3 over here, so I can scratch out that 4. If I've got 1 in the middle and 2 in total in this intersection, that means there's 1 there. Same thing here, 3, I've already got 1, so that 3 means there's got to be 2 over there. Once I've now got everything except for 1 unknown in each part, so I can just do some simple math there of adding up 1, 1, and 3. I know I need to get to a total of 7, so I know that it has to be 2. All right, so we've got 2, 5, 6, 7. Same thing for dog sledding. We've got 5 and 6, total of 6. So that means our dog sled has to be 5. And our skiing is total of 10. Right now I've got 4, so I need to have 6 in total up there. We're going to go through question 11. So let's see when we get to question 11. Hopefully that will it'll just be another example that'll make it seem clear. Okay, so question 11 says an English teacher took a class survey to determine what books the students had read. Of the 24 students in the class, we find out, so I'm going to set these sets. Say this is the Absolute True Diary of the Part-Time Indian, and then When Everything Feels Like Movies, and then there's the Hate You Give. Okay, and it tells us that there are 11 students who have read the Indian, 7 who watched the movies, and 10 that read Hate You Give. Now, the next thing we do is we look through all of the information we're given, and we look to see if any of the information tells us about what's in the center, because the center is really a key piece of information. If we have that, it simplifies the process of doing the Venn diagrams considerably. So we read through and we see that the very last item they give us is that one student has read all 3 books. So we can put that in the middle. Now we go back and we continue to look through any and statements. And in this case, it looks like all we were given are ands. So it says there are 3 students had read When Everything Feels Like Movies and The Absolute True Diary of a Part-Time Indian. So that's the intersection between the movies and Indian. We've already got 1 in that place, and they're telling us that there are 3 in total. That means we have 2 left over there. Then we're told there are 4 students who have read the Indian and Give. So intersection between Indian and Give. So that's here. And if there are 4, we've already got 1. So that takes us down to 3 in the remaining area. And then we're told that there's 1 student who's read Give and movies. So again, we've got the intersection between Give and movies. There's only 1 student that's in that space. So that means that the remaining space here has a 0. Now the process is just straightforward subtraction or addition, whichever way you prefer to go. We need to end up with 7. We've got 2 and 1, so we've got 3. So we just need to add in 4. Similarly with Hate You Give, you've got 10 is your total you need to reach. We've currently got 1 and 3, which gives us 4, so we need to add in 6. And Part-Time Indian needs to be 11 in total, but we've currently got 5, 3, or total of 6. 2, 3, and 1 make 6, which means we're missing. So this one was a lot more straightforward because they gave you the center position right away. It simplifies the process of finding all of the other pieces. So once we've got the Venn diagram, we can then go ahead and find the probability that they're asking for. So they're saying if 1 student is chosen at random, what is the probability that the student had not read any of the books? Well, I forgot to do the final step of this. So my total sample space was 24 students. I didn't do my final check to see what happens when I add up everything that is in my diagram here. So if I add up all of the individuals here, I've got 6 and 4 is 10, 5, 2 and 3 is 10, and 1 makes 11. So I've got 21 in total, and I'm supposed to have a total of 24. So that means I have to have 3 that are left outside. So based on that information, what is the probability that somebody hasn't read any of the books? Well, the answer was in the final step. Probability that somebody has read none, 3 out of 24 or 1 out of 8.